Hey, this is Leach with Simpson Math, and in this video, I'm going to be talking about correlation and linear regression, answering some kind of common questions that students might see. The main focus for this video is my business stat students. So let's get started by talking a little bit about R squared. So the R squared, it's literally what it sounds like. We take R, we square it. So if you recall, R is the correlation coefficient. It is a measurement of strength between the x variable and the y variable. It is a contextless, unitless measurement. It doesn't matter if we switch x and y. It doesn't matter if we change the scale. So like if I swap from measuring the relationship between height and weight, but I switch our measurements from height from inches to centimeters or to meters or whatever, it doesn't matter because it's the relationship between x and y. So R is a measurement of a relationship between x and y. Then if we take it, we square it, we get a really interesting value. We call it R squared. I'm going to show you like a different way of calculating R squared just for knowledge, but really at the end of the day, we're just going to be taking R and squaring it. But it fascinates me that we're going to see it as the ratio, the one minus the ratio of two different variances. But first, let's take a look at what you see on the screen. With this, on the left-hand side, I have the relationship between a linearly perfect relationship. My go-to example for that is if you had a pizza place, they have one size pizzas, and it's 50 cents per topping. It doesn't matter what topping it is. Every additional pizza you get, it adds 50 cents to the cost of the pizza. So if I have an example of some randomly selected pizzas and the number of toppings and their cost, so we have number of toppings and then the cost, it would be a perfect linear relationship. No dots would deviate from the line. All those residuals would be zero. So the measurement of linear strength, the correlation coefficient is 1. If I square it, I would also get 1. But we'd like to report our R's in terms of a percentage between 0 and 100%. We'll see what that is in a second. But so we like to do it as percent. So here's how I would say this. I would say 100% all of the variation in our cost, every single reason why our y values went up or went down, every single change in the y value is accounted for by the regression of the cost of the number of toppings. So regression of the cost of the number of toppings is basically the relationship between x and y, our linear relationship between x and y. So 100% of the reasons why cost goes up or down is because of this relationship that we observe, this linear relationship we observe between cost and number of toppings. Again, this is not implying a causation, just a numerical relationship between these two. All right, so there's a perfect linear relationship. Let's jump to the other end of the spectrum, and that's where there's no linear relationship. So let's say I take the height stuttering, height of an employee, and I ask how long it takes for them to commute to work. So I take their height and their commute. Now I'm just making up this. I just made up the numbers, put the cloud, put a dots in just kind of a cloud. But I would expect there to be pretty close to 0. There should not be any observable linear relationship between height and commute to work. Taller people don't commute further, or shorter people don't commute further. There's no relationship between those two things. It's a little bit of a nonsense thing to ask. So that R would be 0. If I square 0, I get 0, but we report R squared as a percent, so it would be R squared percent. So then I would say 0% is none of the reasons why. So if I take a look at my commute to work going up or down, 0% of when the commute to work goes up or down is accounted for by the relationship between x and y, accounted for by the regression of the commute to work on the height of the commuter. Like never ever ever does this relationship between x and y influence the changes in the y, because they're not related to each other. All right, so let's take one that has a strong relationship. I'm making this number up. It's a strong relationship, not perfect relationship, because there's a lot of variables at play. But I've heard it reported that it's somewhere around 0.8. So let's just go with it. It's a nice academically sound number. So the relationship between SAT and the GPA. So specifically, the standardized test, the SAT, taken either the senior year in high school and then the GPA that following year, the freshman year in college. We would expect students who score better on the SAT to do better on their GPA, but not necessarily perfectly aligned. And students who do poorer on the SAT will probably have a poorer GPA, because the SAT measures your ability to take that test, some level of your kind of studiousness, how much have you learned throughout high school. And so that does kind of play into how well kind of grades we would expect you to get. But there's a lot of other variables at play. So let's say the R is 0.8. If I square 0.8, you get 0.64. Written as a percent would be 64%. So we would say 64% of the variation, 64% of the Y changing, of the changes in Y, 64% of the variation in the GPA freshman year of college is accounted for by the changes in our X and our Y, accounted for by the relationship between X and Y. Formerly I said accounted for by the regression of the GPA freshman year in college on the SAT senior year of high school. So 64% of my Y's changing is accounted for by the relationship that we observe between these two. So that means that there's 36% of other things going on. You just, depending upon your major, it might be easier or poorer. Maybe life events, maybe too much partying your freshman year. Maybe you're just a really good test taker, but you don't make as good of grades, and so things are a little bit weird. So it's not a perfect relationship. Okay, so let's take a look at a specific problem. This is from my business stats. This is data from a small bookstore are shown in the accompanying table. What is the value of R squared and what does it mean? So if they gave us R, I would just need to square R and I would get 0.9474 if they gave us R. Sadly, when we look at the table, they give us the data values. They do give us the mean and standard deviation, but they don't give us R. So we do need to calculate R. If you check out my previous video, I go through this in a lot more detail. I'm just going to do this on Desmos. You could do this on Excel or on the 84. I'm just going to do Desmos. So I'm going to copy the clipboard, keep it as tab. Command or Control C to copy. I'm going to go to blank Desmos, make sure it's big for y'all. And just Command or Control V for paste. And it even pastes in our dots here. So then to get the regression line, remember our equation, it's y equals, or y hat rather, equals b null for the y-intercept plus b1 for the slope times x. A few little tweaks. Desmos is going to want it to be y1 instead of just y. So I'm going to take y1, just on my keyboard, I press y and 1. When you type a number following the variable in Desmos, it will auto subscript. I have to subscript because my output rather, are these y1s. So we can't stick a hat on here. A hat isn't an option in Desmos. So we're going to say that it's being predicted by that by using the similar to the single wavy line. So just shift and then that tilde above the tab left of the 1, or the on-screen keyboard, you do the ABCs, and here's our subscript if you needed it, and then here's the tilde. All right. And then we're going to do B null, so B sub 0, so B0 plus B1 for our slope, and then X1 because that's our input. And so I'm going to scroll up if I can and press return to outside of not behind my head. And notice we get R. R is 0.9733. And then Desmos go ahead and squares it for us, and we get R squared of 0.9474. For some reason, the software that you're using doesn't give you R squared, but it does give you R. You can just type in the R and then square it. And notice how we do then get accurate out to at least 3 decimal places. The R, if I just square that R, so that's one option. If you don't have the R squared, just type in as many decimal places as you can and then square it. All right. Now I'm going to so at the end of the day, that's all we need to do. We just type in our R squared. It does want a percent. Notice how it says 2 decimal places, but it already has a percent symbol, so it's really a total of 4 decimal places if I'm looking at my Desmos calculator here. So move the decimal place and then report it as a percent. And then what does it mean? So basically it's 2 options, and I'm looking for variance in my y's. R-squared is about the percent of variation in my y's on the model, on the relationship between x and y. So this is percent of variation in my y in these sales, and then this is noticed percent variation in the y's that were accounted for in the model. All right, now if you I'm going to do the next little bit for those who are real curious about R-squared. If you're like, I got the problem, I'm good, then you can go ahead and skip on to the next bit. But I want to talk a little bit about what R-squared actually is. I'm not going to go too crazy about it, but so using the same thing, I just have one already done. So this same exact data, all that I've done is I've actually, if you notice in Desmos, do you see where it says by E1 plot? If you click that, it'll produce the residuals. This is a graph of the residuals, but this one's already kind of set up for us. I do have my x and y's squared, zoom squared, so that way it's on a 1-to-1 scale, because I'm going to want that in a second. So I have my e's, I have them in red for errors. And so these are the residuals. So just to point out, and you do see it graphed down below on the y-axis, notice how this data value here, if I'm looking at the 11s, I have one about 1.5-ish units above and one about a 1/2-inch unit below the line. So if I look here, I have a residual about 1.5-ish above the line and about a 1/2-ish below the line. So I'm looking at my two 11s here. Notice how this residual is 1.34, this residual is a negative 0.65, and that's what this is. All right, so where this line is, where this actual prediction line, if I get to 11, if I plug in 11, y hat is 18.652. If I do 18, I observed 18 minus 18.652, I get that negative 0.65. If I do my observed 20 minus this 18.625, I get the 1.34. So that's what we get here. All right, so those are the residuals. So I want to show you something that I think is interesting. So take a look at R-squared. It's this 0.9474. And if I have this formula, 1 minus the variance in my e's, so if I take these e's and find the variance of them, and I divide it by the variance in y1, I literally get R-squared. I think that's kind of interesting. Now, little disclaimer, E has its own, the standard deviation of E has its own formula. It divides by standard deviation of, divides by n minus 2. It's a little bit different. I don't know if this is Desmos as being smart, if it's the proper proper variance of the residuals or not, if I'm just getting lucky for the first few decimal places, but this is more big picture than a precise calculation. So this is the variance, or at least a reasonable estimate of the variance in my residuals, divided by the variance in my y's, and 1 minus that gives me R-squared. I just think this is fascinating. So if I take R, which if you're called R is the sum of zx times zy divided by n minus 1, that thing that is R, if I square it, I get R-squared. I get 0.99473 or 9474. But if I take 1 minus the variance of my residuals divided by the variance of y1, and the residuals are also dependent upon R, I get R-squared. It kind of blows my mind. All right, so here's a little bit of visual representation about where this comes from. So imagine I took, imagine I took all of these green dots right here, and I just went smush, and just smushed them onto the y-axis. I smushed them onto the y-axis. I said, hey, y-axis, make a box plot of all these dots, and then I pick it up and I plop it down below, and I would get this. Okay, so you see this purple box plot down below. So again, if I took all the green dots, ignoring this line for just a second, I guess I should make this green. Let's make it green. So if I have this green box plot here, if I just take these green dots and I go smush it onto the y-axis, and then I make a box plot out of it, pick it up, and then just set it down. And I'm setting it down so that way the center, the 0 is at y bar, just because I kind of want it down there. That's why I have, oh, you don't see it. That's why I have minus mean of y1 is producing here. Cool. Let me turn that off so we don't get confused. All right, now let's say I take my residuals, all these residuals right here. kind of imagine that they're stuck onto the line, and I just kind of tip it and just kind of slide them down the line, so that way I have dots on the y-axis. Or really even better, take a look at my at these residuals down here, these red dots, and I push them onto the y-axis, and I make a box plot out of them. I would get a box plot that looks like this. So again, if I smush these onto the y-axis, turned it, because Desmos can't make them vertical, it won't make box plots vertical, I'd get this. All right, so what I'm wanting to do is I'm wanting to compare these two box plots. Let me zoom in on it. So I'm comparing these two box plots. What percent of this green box plot, or the green data set, is not being accounted for by this amount of wiggle? Well, that's what's happening here. So if I take this red is the box plot of my errors, of my residuals. This green is the changes in my y. And I want you to notice that the E is a whole lot smaller than this green box. If they were equal to each other, if it was something like the height versus commute we saw earlier, these errors would be the same. All right. And if there was something that we saw where it was the number of toppings of the cost, this error, this residual box, wouldn't exist. All right. So I'm going to show you one last thing numerically here, and I'll tie this together. This is not how R squared is calculated, but I'm using a much more tangible measurement instead of the variance. Let's take a look at the IQR. So let's take a look at the width of this green box. That's the IQR of the y's. Look at the width of this red box. That's the IQR of the residuals. So if I want you to notice that I set this up earlier and it got, oh, never mind. I got confused for a second. So I want you to notice that if I do basically what I'm doing up above, where it's 1 minus the variance of E divided by variance of Y1. But now I'm doing 1 minus the IQR of 3 divided by the IQR of Y1. Q3 minus Q1 of the E's over Q3 minus Q1 of the Y's. So 85% there's like 85% of this green box is not covered by the width of this box. So basically the width of this box is just 15% of the width of this green box. Let me say that again. The width of this red box is just 15% of the width of this green box. That means 85% of this green box is not dealing with the width of this red box. What R squared does, it's not just counting just the quartiles, it's using every data value. Every data value to produce a measurement of spread, and that spread is called the variance. Remember, variance is the standard deviation squared. So this is just a kind of visual representation of that. So that's why we can say almost 95% of the variability in the y's, 95% of the reason why the y changes is related to the changes in the x or the y. So notice this right here, this little bitty size of this box plot is how much was left over when I got rid of the relationship between the x's and the y's. So that's why I can say 95% of the relationship, 95% of the changes in the y's is related to the relationship between x and y. About 5% of the time why the y's change is because of some other reason that we haven't accounted for yet. All right, so I think that's enough rambling for that. Let's move on to another question. All right, this is about regression to the means, using that idea of regression to the means to be able to make some predictions. So it says data from a small bookstore are shown in the accompanying table. The correlation for the data is 0.956, completes parts A through D below. If the number of people working is 2 standard deviations above the mean, how many standard deviations above or below the mean do you expect the cells to be? And what value of cells does this correspond to? We do have our data set. They do give us R, which is the correlation coefficient is 0.956. So I'm not going to need to actually run this to get R, but I will be using the mean and standard deviation of Y in just a second. All right, I'm going to switch to my iPad just so I can talk a bit about this. So this is about regression to the means. Real short of this is that we expect those we expect fathers, taller than average dads, to sire taller than average sons, but we expect those sons to be shorter than those dads. Similarly, shorter than average dads tend to have shorter than average sons, but they tend to have sons that are taller than them. That's the idea of regression to the mean. If there was a perfect linear relationship between two things, if something was 2 standard deviations above the mean in the x, we'd expect the output to be 2 standard deviations above the mean of the y. Recall standard deviations above the mean or below the mean are z-scores. We're about to use those. So again, if something was 1.2 standard deviations below the mean, we would expect it to be 1.2 standard deviations below the mean of the y. Sorry, let me rephrase that. I missed the x. If I had a positive relationship, we'd expect if I go 1.2 standard deviations below the mean of the x, we'd expect it to be 1.2 standard deviations below the mean of the y if it was a perfect linear relationship. But it's not. There's a little bit of weakness to it. I mean, this particular one is still pretty strong. So I'm going to draw a picture that I think might help it out. I'm going to over-exaggerate this. This wouldn't necessarily be true for something that was this perfect relationship here. Or sorry, this pretty strong relationship. So this would be one that would be a little bit weaker. So let's suppose that this is a that's like a y equals x line almost in a way. And let's say that the regression line is something about like this. Oops, I want to have that be a solid line. So let's say that this is whatever my scale is, this is y equals x, and then this is some other line. This is my y hat equals my regression line. It doesn't really matter what it is. And my r is something weaker. Let's say it's like 0.7. Oh no. Okay, my screen, my iPad lagged transferring that data over. Okay, so what's going to happen here is right here in the middle of all of this, let me get this dotted line. Can this dotted line be seen? Oof, barely. Let me use this dotted line then. So in the middle of all of this, this is my x bar, this is my y bar. All right. So if somebody had, if I would expect a dad who is average in height, they will tend to have a son who is also average in height. All right. Let me draw this. Let me do a dad who's 1 standard deviation above the mean. If someone was 1 standard deviation above the mean, so this would be my x bar plus an s. What would happen is notice I would expect this dad, if this was a perfect linear relationship, I would expect this dad to also have a son that was 1 standard deviation above the mean. The problem is that's not going to happen. We're actually going to have this dad's going to have a son who is or I keep saying dad's having a son just because that's the context. It would be a lot stronger relationship between this. But if I have just an x value that is 1 standard deviation above the mean, then we would predict that we would have a y value that was r times point r times r number of standard deviations above the mean. Visually, this is going to bug me. This is probably an r that is like 0.4, pretty weak. I just need to change my graph because I made it real shallow. So let me draw this again. Let me draw this with pink. So if I have an x value, there's 1 standard deviation above the mean. My prediction, notice, is not 1 standard deviation above the mean of the y. If it was 1 standard deviation above the mean of the y, it would be this. This would be, that's my 1 standard deviation above the mean. But notice it's not. It's like this distance right here. I'm pointing to this distance between here and here. Oh, that's a little short. This needs to be up just a hair. There we go. I'm pointing to this distance right here. Notice that that distance is about r. Specifically, really, r times s. All right? If something was, let's say, let me do an example down below. So if I had 2 standard deviations below the mean, so if I was 1, 2 standard deviations below the mean. This is S, this is S. So this would be x bar minus 2 standard deviations below the mean. Let me change this picture to being instead of an S, instead of a 1, this could be an S. All right, well, what do we expect the y value to be? Well, we'd expect the y value, if this was a perfect linear relationship, the y would be all the way down here, would be at 1, 2 standard deviations below the mean of the y. Well, that's not the case. In this case, we're going to expect the y to be right here. It's going to be, the y is going to be all the way up here. Oops, I was off a little bit. All the way up here. And so notice this is about 1, oh shoot, I just closed my stuff. Was this the one that I was on? No, I was on this one. Okay. On my graph here, this would be about 1 standard deviation below the mean. And so I'm actually going to be going, this distance right here is specifically going to be r, again, r times 2s. I'm doing 2 standard deviations because it's this, because I'm going 2 standard deviations. So in this case, if r was 0.4, in this particular case, we're going to have 0.4 times 2s, or in this case, 0.8 times 2s. And in my scale, if you're seeing my lines, if you're seeing that this is that this right here, from here to there, is one unit, do you see how I'm at about 8? Notice here, if this was r is 0.4, and I'm at 1 standard deviation, so notice that I'm at 0.4 of a standard deviation to get to this upper one. All right, so now let's answer this question that we have going on here. This says that if the number of people working is 2 standard deviations above the mean, how many, there, now you can see it. If the number of people working is 2 standard deviations above the mean, how many standard deviations above or below the mean do we expect sales to be? The gist is, there's this formula. Our zy, the z-score of my y, the number of standard deviations above or below the mean, we expect it to be r times zx. All right, so the predicted number of standard deviations we expect the output to be in the y direction is equal to r times the number of standard deviations we expect the data value to be above or below the mean in the x. So in this particular case, if our predicted zy hat, if we're r standard deviations, well, r is 0.956, and I'm 2 standard deviations above the mean, so that's a positive 2. So the z-score itself is going to be a positive 0.956. Oops, I didn't actually multiply. Silly me. Let me grab my calculator. 0.956 times 2. And I'm going to get 1.912. That's better. So if I multiply these two things together, so if a data value that is 2 standard deviations above the mean of the x, we expect them to be 2 standard deviations above the mean in the y. So that's why we get 1.91, 2 decimal places, and it's above the mean. All right, my options here were I filled in the blank with whatever number it is, and then I have above or below. Since it's a positive z-score, then we're going to put in a positive, then we're going to have it above the mean here. All right, I'm going to skip B for just a second. Let's do letter C. If the number of people working is 1 standard deviation below the mean, how many standard deviations above or below the mean do we expect the sales to be? Right? So following that same train of thought, right, what's my zy hat going to be if they're below the mean by 1 standard deviation? So again, my r is 0.956, and I'm going to multiply by a -1 because it's below the mean. So if I do that, I get a negative 0.956. So since I'm below the mean, I'm going to say below, and I know it's below because it's negative. So let me restate that. Since my z-score is negative, I know that I'm below the mean. But when I answer this question, like I live in North Temple. I'm 3.1, 3.2 miles away from Temple College. So I'm going to drive south to get to Temple College. So if I'm driving south, do I say I'm driving in negative 3.2 miles to work? No, I'm driving 3.2 miles to work, and it just happens to be south. So that's why my answer here, I'm going to say that sales should be 0.96. I'm taking this 0.96956, rounding it to two decimal places, 0.96 standard deviations below the mean. So I don't write negative here, because this is a distance. This below here is taking care of the direction, which was the negative symbol on my z-score. All right. Now, oops, go back to it. Now let's take a look at making a prediction in context. So what value of sales does this correspond to? The number of people working 2 standard deviations above the mean. They're 1.91 standard deviations above the mean. Sales should be about what? All right. So I'm going to show you 2 different ways of working this. The first one is conceptually, let's just talk about z-scores, because that's what we're doing here. Recall that a z-score formula is z equals some x value, some observed value, minus the mean over our standard deviation. I'm going to make 2 adjustments because I'm talking about y values. This is the number of my x is 2 standard deviations up. I'm predicting about the y. So I'm going to change this to be y and y hat. I'm expecting y hat. I have an expected y hat that I'm trying to figure out. I have an observed y that I want to know about. All right. So then, and then my standard deviation is then it's the standard deviation of y. So we're wanting to know about, ultimately we're trying to figure out this predicted value of y right here. So my brain just stopped for just a second. Should have written this out before the video. Oh, that's what's bugging me. So in general, it would be y minus y hat, but specifically here, this is going to be y. I'm actually going to be doing y hat and then a y bar, because let me go back to my picture. So this pink right here, these pink spots would be my y hats. This right here would be my y hat. Oh, yeah, my y hat. And notice I'm trying to predict a y in relationship to y bar. All right, I'm sorry I got confused about my y bar and my y hats. So just a reminder, it would be x minus x bar is my normal numerator. So I'm replacing x bar with a y bar because that makes sense. Instead of my mean for the x's, it's the mean for the y's. But then in this case, instead of observing just an actual observed y, because we're not talking about that, I'm talking about my predicted y and its z-score. All right, I was like, that for me didn't look right. Okay, so I'm going to highlight what I want to find. I want to find y hat. I need to get that by itself. So what I'm going to do is I'm just going to solve for it. I'm going to kind of solve it while keeping the standard deviations, the sy, the y bar, and all those symbols there. And I can go ahead and call this zy because it's that specific zy. So what's going to happen here is, let's say if I was going to solve this, which if this is bugging you, let me go ahead and drop in the mean and standard deviation. So we know that the z is, for the first problem, is going to be 1.912. Our y hat is what we're looking for, minus our y bar is 18.1, divided by the standard deviation is 5.51. This freaks a lot of students out, sometimes just solving for y bar. Solving for this y hat. But if you're seeing it this way, it's like, oh, it's numbers. I can be able to do that. And further, if that's freaking you out, round them for just a second. So if I had that equation, and I said solve for this y hat, and if it's freaking out that's a y hat, just make it be a y for a second. If I just said solve this for y, you would, I think most everyone watching this video should be able to know, oops, that'd be a 6. And so we'd get 12 equals y minus 18. So we'd multiply both sides by 6, add the 18, and then we would end up with 30 as the y. Does that make sense? So we're doing the same thing, but I'm just going to do it in symbol form so I can kind of give myself a little formula here. All right, so I'm going to multiply both sides by the standard deviation of y. Notice in our formula, in our work, we now have a standard deviation of y times the z-score for y, because the z-scores are the number of standard deviations, the values above or below the mean. And then now I'm going to add my y bar, because I'm going to get the y hat by itself. I'll put the y bar first, because it makes sense in my brain to do that. And then I'm going to just move my y hat over to the front, just so that we kind of have like an equation, or a little formula looking thing. So let's take a look at this. My predicted y value, I'm going to start at my mean for my y, and then add the number of standard deviations that the value is above or below the mean. So if I'm one standard deviation above or below the mean, I'm going to jump one standard deviation. If I'm two standard deviations, I'll jump two. If I'm a negative 1.2, I'll go down a negative 1.2 that way, or go down a 1.2. So in this particular case, we now have this formula. So let's replace y bar with the y bar 18.1. And just so you know where I'm getting that from, that is from our formula, from our data. Data is right here. Here's our y bar, standard deviation of y. So my y bar plus standard deviation is 5.51 times our number of standard deviations. What we saw earlier in part A, it would be 1.912. So you could use a 1.91 like what we rounded to earlier, but I'm going to go ahead and use all the decimal places that we have just because I like to do that because it's better. And when I do my multiplication, 5.51 times 1.912, and then add that to 18.1, just doing it in my calculator off screen, 28.635. I get, oops, I need more decimal places. Why am I off? 635. 5.51, 18.1, 28.635. Sure, I won't do the full decimal places. 1.991 times 5.51, and then add the 18.1. That's strange. Normally it will have it right, but it does have it within the answer tolerance. It'll be a little bit high. It's late and I'm on camera. Okay, so we have our 28,264. So let me do this math on camera now. So on here, I'm taking my mean, which I'm taking my 5.51, multiplying it by 1 point. I'm just going to do the 91 that is over there, and I get this 10.5241. I'm going to add our mean of 18.1, and I get 28.264. Well, notice it needs to be in thousands of dollars. This is $28,000. So I'm going to, if you need to do it, you could just say times 1,000 or move the decimal place over 3 times. That's where we get 28,624. I'm just going to check this one time on screen. So if I'd get 5.51 times 1.912, and then I add that to 18.1, yeah, that is bigger than the answer tolerance. I need to say a thing or two to Pearson about this one, but I'll lose it when I move on. Oh well. Okay. All right, so then we're going to do something similar for letter D. So D is if I'm one standard deviation below the mean. Let me get my calculator back. One standard deviation below the mean. So then I'm going to now take my standard deviation of 5.51. I'm going to multiply it by a negative No, I don't want to negate u. Multiply. Ugh. Clear. 5. Clear. Just blah, blah, blah. I'm going to type in 0.956. I'm going to negate it. Now I'm going to multiply by my 5.51. And then I'm going to add that to the 18.1. And notice this is 12.832, but my unit in my y's is thousands of dollars. So 12, so move that over. So I'm going to do times 1,000. And I get this number, and this one does match. It is within that answer tolerance. So then we get 12,832 is what I would say. They probably, I guess if you use the 96, then it would be that. That's a little bit interesting that it's that off. Shruggies. Okay. There's that one. Next, we're going to do... These last two don't have any need for any tech. There's just a few things I wanted to talk about real fast. On number 12, this one here, I just wanted to talk about the number of text messages. This question's a bit dated because, in case you're like, why we have a limited number of text messages. At some point, we had to pay per text message. So back in the day, if it was number of text messages and cost, that would be a pretty linear relationship. My number of text messages was explanatory variable. Cost was my response because this determined number of text messages determined cost. And it would be pretty strong, it'd be pretty positive, and it'd be definitely positive, and it would be linear because it would be like 10 cents a text message, and then like 5 cents, 1 cent, and then eventually became unlimited. Because now we have data, and then we care about speed now. So it's a whole thing. So there's that one. I just wanted to point that out for you, Jen, whatever you are now. One that's interesting is this last one, is that the price of a product and the number of products sold per day. So the more you price a product, the demand for it's going to go down. Supply and demand curves. So the higher you price something, the less that you would expect to be sold per day. So it's going to be a negative direction. But what's interesting is that this is true. It would be in a narrow range, it'd be pretty linear, but in a curved, but it would be rather curved in a larger range of prices. Because as the price grows, the demand for it's going to go down, but not necessarily go to zero. So it's going to have kind of a curve to it. And then even if you price it super duper duper cheap, in theory it could kind of skyrocket, but you're not going to go negative. So it's going to have this kind of curvy thing. But if I just look at it over a short range, it would then look pretty linear. So that's that. So in a short range, pretty long, but if I do pretty linear. But if I do it in a long range, there's still going to be some demand for it. Probably in theory, it might hit to zero, but it's going to be getting closer to zero. And then eventually kind of definitely curving down. All right, that's all I wanted to say about those. And then this is the last one. All right, so is there a relationship between total team salary and the performance of football teams? For a season, a linear model pricing predicting wins out of 16 regular season games from the total team salary in millions of dollars is shown below. Complete these parts. So we have wins hat, the number of wins won by this team, by this football team. So the predicted number of wins is 5.298. This is the y-intercept plus the slope of 0.027 salary. So this is times the total team salary. So if I add up all the players, the total team salary. So our explanatory variable, salary, because salary is being used to predict the number of wins. We know this also to be true just because it's our input, so that's salary. And then again, we're predicting wins, that's why it's wins hat. It's predicted wins, so that's why that's kind of obvious there. The response is the wins because it's being determined by the total salary. So this is what we're trying to see is the relationship between salary and wins. Salary would be the driving force. More salaries should drive up the wins because you might get better players. What's the slope? The slope is this 0.027. So notice this is making sure that you know which one's the slope versus the y-intercept. The 5.28298 has nothing to do with slope, so I can eliminate A and D. So on average, teams who spend 1 million more in salary win 0.027 more games. I'm going to go to my iPad and talk about this for just a sec. So let me write down slope. Slope is this, 0.027. We're used to slope being rise over run, or the change in y over the change in x. That's what we're used to. We're used to this being some sort of fraction. Well, how can I get a fraction out of this? Don't think hard. Right? Just take the number over 1. 0.027 over 1. Well, what's the units on here? So this is, remember, it's rise over run, so the y value is my wins, because I have wins hat is the 5.298 plus 0.027 times the salary. So wins is number of wins, it's salary in millions, right? So what this is saying is my y value is wins over salary in millions. Okay, so let me point to this. For every additional $1 million in salary, the model predicts an increase, because it's positive, an increase of 0.027 wins. And do that again. For every one additional $1 million in salary, the model predicts an increase, because it's positive, 0.027 more games won. All right. Sometimes, now, that is what the question, that's what letter C has. So, on average, teams who spend $1 million more in salary win 0.027 more games. Just a note here, do you see that on average? You heard me say a second ago, the model predicts, or we expect, or something like that. It's what I call a fudgy word, because it's not a deterministic thing. If a team, it's like, oh, if you want to win more games, just spend more money. 1 million more dollars spent on salary will make 0.027 more games won. No, because you can't even win 0.027 of a game. Also, winning 0.027 of a game is kind of weird, right? It's so small that's a little bit untangible. So let's move the decimal place on both the numerator and the denominator over to the right by 1. So if I have 0.27 divided by 10, so what I did, this decimal place went over, this decimal place went over, so 0.27 over 10. So again, this would be wins, still wins, per salary, again in millions. So for every $10 million spent, the model predicts an increase of about a quarter of a game won. Do that again if you want to. For every 2.7, so that's 2.7 wins over 100 million. So for every $100 million spent in salary, the model predicts an increase of 2.7 games, 2.7 more games won. Okay, that might make a little bit more tangible sense there. All right, let's go back to the question. What is the y-intercept in this context? We know it's 5.289. If you answered this right, none of the options should be 0.027. They're all gone. So it should be that. But notice the it's my y value is not about money. It's about wins. That's why I can get rid of B and D. It's not $5.298 million. It's $5.298 wins. So this is the base value, or in this case, it's the base number of games won before we start looking at salary. But it's not really meaningful because they're not going to, they pay these players. It's not going to be 0. It's going to be quite far from 0. So that's why we say it's not meaningful. Often the y-intercept is rather not meaningful unless we have data that is right up on 0 or even negative. Often it's kind of outside of our scope of our data, so we don't really want to extrapolate to that. But it is that base value is kind of where it's starting. And noticeable, it's not going through 0. If one team spends 12 million more than another on salary, how many more games on average would you expect them to win? don't overthink this. Some students have a hard time with this because they're wanting to like look at the data, look at R, or do all sorts of other things. Notice what they're not giving you. They're not giving you the data. They're not giving you the mean or standard deviation. They're not giving you R. You just have this, and this is able to figure out. So I like to almost think about like my line here. It doesn't matter at what point I pick. If this other team has spent 12 million more, so if I go up 12 million on my X, how much more are we expecting to go up on the Y? So one of two ways of working it. The long way is plug in some number for salary, look at the wins. Plug in some number that's 12 million more for salary, look at the wins. That'll do it. But really, when I compare those two, when I subtract those two wins, it doesn't matter where this 5.289, I keep saying that, 5.298 is just going to get subtracted out. So really, I just need to plug 12 into this 0.027, and I'm going to get 0.324. Let me demonstrate that. So the formula, the wins hat formula is 5.298 plus 0.027 times x for salary. And I'm going to go ahead and just say this is f of x, so I can use function notation. So I could say I have f of x of some team that's been, not f of x rather, I have f of some team that is at 20. They spend $20 million, then they're going to expect to win 10.698 games. Cool. If I then was 12 million more, that'd be f of 32. So if they spend 32 million, 12 more, they get 13.938. I could just subtract those. 13.938 minus 10.698, and we get 3.24, which is our answer, 3.8. I am off. Oh, no. Oh, that's why I'm off. 0.027. There we go. So now that's why these numbers are off. So 6.162 minus 5.838. There we go. Now I'm at 0.324. Additionally, I could have just said f of 32 minus f of 20, and I would get that same thing. Even if I messed it up, it would then update live for me. But as I said, the easier answer to do is just to take 0.027 and multiply it times 12. And I'm going to get that same number, because notice when I did f of 32 minus f of 20, this 5.298 just gets subtracted. So you can just think about it logically, pick some spot, go up 12, find that difference, but it really is just times slope, just times the slope. If a team spent 130 million on salaries and won 9 games, would they have done better or worse than predicted? Well, let's plug in 130 million on salaries and see what they would get. So I have there, if there's 130 million, then I'm just going to plug in 130. So I'm just going to do f of 130. Oops, you can't see that. I'm going to get rid of these things. We don't need this. Bye-bye. So I do f of 130, or you could just type in 130, and we get the same thing. So we would get 8.808. That's how many games we're predicting to win. So that's this number here. The team would have done better, because if they actually won 9 games, but they're predicted to win only 8.08, then they did slightly better. What were the residual from the team in part F be? Well, 9 minus 8.08, observed minus expected. Notice that's a positive residual. We're going to get 0.192. Let me go to my calculator, my paper, whatever this is, my iPad. I've been teaching stats for pushing almost 2 decades now, generously rounding up. But I have a master's in mathematics. Every time I want to think about residual, I'm going to say resid or E equals, and I'm going to write observed minus expected. This is the same thing that the deviations are, or O minus E. I'm going to do one of these two things, mix and match them a little bit, but in my observed minus expected. So then my residual, what is my observed in this case? A real Y. What's my expected? Or really my predicted? So it's my Y hat. So E is Y minus Y hat. So looking back at this problem, if my observed, they actually got 9 wins, but we predicted 8.808. So if we do that subtraction, that's how we end up with a positive number, big minus small, and we get the 0.192. All right. And also just from another question, would this be an over or under estimate? So a positive residual is actually an underestimate. This residual is from the point of view of the regression line. The regression line is having to look up at the real data, so that's why it's a positive number. The over-under estimate is from the point of view of the dot. The actual data value, 9, is looking down at the estimate, is below it. That's why it's an underestimate. All right, I think last question. The residual standard deviation is 3.03. So when we showed you this earlier, if I showed you just these red dots right here, those are the residuals. If I find the standard deviation of those residuals, that's what we're talking about. So I'm giving you the standard deviation of the residuals is 3.03. What does this mean practically? Well, in the practical sense, this is not really useful. Our book doesn't talk about it a lot for some reason, but when we talk about standard deviation, there's something called Chebyshev's rule. It's Chebyshev's theorem that it doesn't matter the distribution, if I go up, if I'm standing at the mean and I go up 2 standard deviations, down 2 standard deviations, it doesn't matter the distribution, that is at least 75% of the data values should be within those 2 standard deviations. Later we'll be talking about a bell-shaped unimodal symmetric curve. That's going to be about 95% of the data should be within 2 standard deviations of the mean. So generously, most distributions should probably somewhere be between 85-90% of the data value should probably be within 2 standard deviations of the mean-ish, at least. It should always be will always be at least 75. But in many of these cases, it's still probably 80-90% or so. So the 80-90% of the cases are between these two values. So in this case, if my standard deviation, the residual is this 3.03. So that's a plus or minus 6 games. So if I go down 2 standard deviations, so down 3 games, down another 3, that's losing 6 games. Up 6 games, up another 3, up another 3, up 6 games. That's a plus or minus 6 games. So notice here, so they're just saying, picking 8 out at random. If 8 games are predicted, that's 2 to 14 games. If 9 games are predicted, that's 3 to 15 games. That's a really big spread. That's pretty poor prediction power because there's so much variability in the Y. That's what's happening here. So basically, there's so much variability in the residuals that's not accounted for by this relationship because the relationship is so weak, basically. That doesn't have good predicting power because the standard deviation is large compared to our data values. All right, that's what that is. Those are just some weird things. I wanted to cover that. Yeah, so I think hopefully that helps a little bit more. If you're in my current class, and as always, if you need help, hit me up on Discord. And if you are in my class and you're like, oh, I wish we would talk about another video, another problem, or I'd ramble about another one, make sure to let me know. I can always record more. Otherwise, I hope this helps, and I will see y'all in the next one. Bye.